A constant source of blood glucose is an absolute requirement for human life. That is why the body developed mechanisms for storing a supply of glucose in a rapidly mobilizable form, namely glycogen. These mechanisms are glycogenesis, the conversion of glucose to glycogen for storage, and glycogenolysis, the conversion of glycogen back to glucose for utilization. Let's first discuss glycogenesis, which is composed of 4 steps. Step 1. The synthesis of uridine diphosphate glucose. It is synthesized from glucose 1-phosphate and uridine triphosphate acted upon by the enzyme UDP glucose pyrophosphate, forming now your uridine diphosphate glucose. Step 2. Synthesis of a primer to initiate glycogen synthesis. Since adding UDP glucose and other glucose molecules to elongate the chain via glycogen synthase cannot occur, a primer should be first formed. A protein called glycogenin can serve as an acceptor of glucose residues from UDP glucose. Glycogenin itself can catalyze this reaction because it is an enzyme. Just add few more molecules of glucose from UDP glucose, producing a short alpha-1,4 linked glucosyl chain that can serve as a primer that is able to be elongated by glycogen synthase. Step 3. Elongation of glycogen chains. You can now add molecules of glucose from UDP glucose at the non-reducing end to elongate the chain via glycogen synthase. It is the enzyme responsible for making the alpha-1,4 linkages in glycogen. Step 4. Formation of branches. The branches are made by the action of the enzyme amylo alpha-1,4 to alpha-1,6 transglucosidase. It removes a set of 6 to 8 glucosyl residues from the non-reducing end of the glycogen chain, breaking an alpha-1,4 bond, and attaches it to a non-terminal glucosyl residue by an alpha-1,6 linkage, resulting to a new non-reducing end. You can now repeat step 3 and 4 to form a highly branched polysaccharide named glycogen. Now let's go to glycogenolysis, which is composed of 3 steps. Step 1. Shortening of chains. The enzyme glycogen phosphorylase cleaves alpha-1,4 glycosidic bonds between glucosyl residues at non-reducing ends until 4 glucosyl units remain on each chain before a branch point. The remaining structure is called limit dextrin, and phosphorylase cannot degrade it further. Step 2. Removal of branches. The branches are removed by the debranching enzyme. First, it removes the outer 3 of the 4 glucosyl residues attached at a branch. Next is, it transfers them to the non-reducing end of another chain, increasing its length. The remaining glucose residue attached in an alpha-1,6 linkage is still removed by the debranching enzyme, releasing it as free glucose. This glucosyl chain is now available again for degradation via the enzyme glycogen phosphorylase. Step 3. Conversion of glucose 1-phosphate to glucose 6-phosphate. Since the glucose released by glycogen phosphorylase is still in the glucose 1-phosphate form, it has to be converted first to glucose 6-phosphate via the enzyme phosphoglucomutase. In the liver, glucose 6-phosphate is transported into the endoplasmic reticulum by glucose 6-phosphate translocase. Here, the glucose 6-phosphate is converted to glucose via glucose 6-phosphatase. Hepatocytes release this glycogen-derived glucose into the blood to help maintain blood glucose levels. However, in the muscles, glucose 6-phosphate cannot be sent into the blood because of the lack in the enzyme glucose 6-phosphatase. Instead, it enters glycolysis, providing the energy needed for muscle contraction.